In this clip, we'll look at a common enough example of a type of function that'll show up fairly often. So f of xy is the square root of 1 minus x squared minus y squared. Or you can write this as square root of 1 minus the sum x squared plus y squared. Okay, so what do we notice about this function? So what we want to figure out, like when we're given a formula or something like this, we want to be able to study it and understand what are its properties, what is the shape of the graph, and like how to plot it, and maybe things like what's the maximum and minimum value and so on and so forth, right? So if you were going to try and, so we haven't really, this is the first that we're talking about trying to plot a function. So one thing I might notice is that we associate the vertical axis with f. So if I write this as 1 minus x squared minus y squared in the square root equals z, and then I square both sides, and then I move the x and y parts over to terms over to the other side, I get a formula which is fairly familiar. This is the unit sphere. So I know that this equation here that I've just drawn corresponds to the unit sphere, so the skin of that ball right there. And then since I was looking at the positive square root of it back at the beginning, it must be the case that the graph of f, so now here's the f axis, f is a function of x and y, it must just be the positive hemisphere, so the top of the dome right there. Now, that's maybe a bit of a contrived example because it turns out to have this nice relationship with a familiar equation. What if it didn't? How would I go about understanding that? Well, we'll talk in a moment about a couple of ideas, namely looking at traces. So this would be, say, let's look at f of 0y. So this corresponds to fixing the value of x equal to 0. Actually here, it'll be better for illustration if I do it the other way around and fix it equal to, fix y equal to 0 first. So now, let's see. Here's my x-axis, here's my y-axis. So y equals 0 is this sheet right here. And so I want to look at the intersection with that plane, y equals 0, because I've got y equals 0 in my formula here. And algebraically, that corresponds to looking at what happens when I set y equal to 0 in the formula, which is I get 1 minus x squared. And so using single variable calculus, because now we have a function of a single variable, so we've reduced it to a question that we understand from a previous course. And so then I could sketch and figure out, oh, it looks like that. Actually, you know what? Let's make that blue. It's in the blue plane. And then similarly, if I did another trace, a trace with setting x equal to 0, then this is going to be 1 minus y squared. And so here's the x equals 0 plane. And so I find that trace right there. And now you can sort of start to see the shape of the graph coming in. So this is the idea of traces. We'll talk more about this in an upcoming clip. I just wanted to give you a quick preview. We could also look at level sets. So a level set is where instead of fixing a value of an input variable, you fix the value of an output variable. So we could say, what's the level set where f of xy is equal to 0? Well, then that means we're looking at 1 minus x squared minus y squared being fixed equal to 0. Now we've got another equation to play with. And this looks like, well, I could square both sides. And then I could move the x and y terms over to the other side. And I get the unit circle. So then that's telling me that if I look at the graph of this function, and so here's f. So if I'm looking at where f is equal to 0, that means I'm looking at this plane right here, and it looks like the unit circle. And sure enough, that's in line with what we saw back in the previous one. It looks like that would connect those dots over there in purple. Okay, so that's the idea of a level set. And so we'll come back to looking at those later. For now, I wanted to introduce this hemisphere example so that I can talk about two important terms for what comes up next. So, namely, look at the fact that this formula that we're given here, this one makes no sense for x squared plus y squared bigger than 1, because then we would have a negative sign in the radical. So that means that the domain cannot include any points with x and y greater than 1. What is the domain? Well, the domain of this f, this is the set where the function is defined or where it makes sense. So it's a subset of values that are inputted into the function. And we need it to be the case that x squared plus y squared is bounded by 1, or it won't make sense. Then there's also, you might have noticed that the square root of 1 minus x squared minus y squared is always non-negative, because we're taking the positive square root. And it's also bounded by 1. If you go back to the picture that we drew before, it's this hemisphere, and the highest point on it is this point at the peak right above the center here. And that happens at height equal to 1. Okay, so this function only takes values between 0 and 1. So we would say the range, oh, and I wrote that a little crooked, of f is all of the, actually let's call it z's. Z in R, where z is between 0 and 1. And that's a really long way to write it. Usually we would just use the standard shorthand convention. The closed unit interval from 0 to 1 is the range of this function. Okay, so more generally, for the definition, we have that for some function from Rn to R, the domain, so now I'm writing the official definition. The one I gave you before was just an example specific to that function, right? The domain of f is the set D where f is defined. And is defined, that might be because I tell you that's where it's defined, or it might be just because that's the only place where it makes sense. So you should, if it's not specified, take the largest set where f makes sense to be the domain. And then you might also want to consider reality for word problems. So sometimes they'll be based on the setup of a problem, you can rule out certain values. Okay. And then we have the definition of the range. So the range of f is the portion of the codomain and I'll just use a regular R to denote it. And this is going to be of the set of values attained by f as it varies over its domain. So, in other words, z is in the range if and only if z is f of x, y, it's f of some point in the domain. Okay. There's no general rule to find it. So it's one of those things where, if you're asked what the range of a function is, you just kind of have to get your hands dirty and take a look. If you can figure out that the function has a maximum or a minimum somewhere, that might help you find the range. One thing that also helps is to look at the boundary. And if you look back at some of the earlier clips, you'll see that this is the kind of thing that I was doing before. I would look at the boundary where there's an equality satisfied, and then try and go from there.